Okay, so hello everyone to the lecture number 11, probably, yeah. Instead of recapping, we ended a chapter on the previous lecture, so I won't recap it. We did some diagrams, although it maybe wasn't warranted, but we gave it a spin, and we draw some diagrams just to have a taste. And we also have some discussions about interpretation of diagrams and virtual process. Just
the essence of drawing diagrams.
The diagram I can show you.
Okay, so we have
no recap.
We're in a tangent.
No recap. Therefore, we will do recap. It's always these were our diagrams, very linear diagrams, no structure, because it was just basically we shouldn't do it, but we tried our best. We talked about that, virtual transitions, diagrams. I mean, I plan to come back to virtual, what it means, because that was inspiring for me. There will be good point probably on the next lecture to talk about it. But anyway, so today we begin the next chapter, famous or maybe infamous, I don't know, Schrieffer-Wolff transformation. It will unfold what it is, what its purpose. But first let's start with something completely different for part 1, diagonalization. So Schrieffer-Wolff transformation, but first it's something else. Maybe related? It is related, of course, but you don't know. We are spinning here a story. So, Hamiltonian, the generator of our dynamical laws of the evolution operator, is an Hermitian operator. Therefore, it is it can represent some observable, right? Typically, we say that it is an energy, observable of energy, and it's kind of works, I guess. Hamiltonian is an observable. Observable H. Okay, so this is energy. Energy. Jesus Christ, I am dyslexic. God damn it. It wasn't that bad a couple of years ago.
You just realize that you are dyslexic and you allow yourself to be dyslexic.
Maybe that's
how it works.
Because I was, usually I'm ashamed of doing stuff like, not being able to spell something. But you know what? It's to live is to be cringe. So I just embrace being cringe.
English is a word. It's an awful language.
Yes. Yeah, I mean, also that. Although you don't want to see me spell stuff in Polish, that would be even worse. I mean, even experts have trouble. It's just a silly language. Okay, so if it is a observable, it has a spectral decomposition, right? Oh my. At some point, this digital pen, it will run out. There is a knob at the end, and it's getting...
We can buy it.
Yeah, there should be some replacement in some box, but it's getting shorter and shorter. There is a... it's like in pencils. Thank you.
How many physicists does it take?
To figure this out.
You need an actuary student.
Christ, that was... Okay, so we won't run out in the
I
end.
just wanted to make sure we can have more lectures.
Oh, maybe not. You should sabotage it. So we have some eigenvalues, the spectrum of H, and we have projectors associated with those eigenvalues, right? So now, if we suppose that we actually know this spectral decomposition, or in other words, we were able to solve for our Hamiltonian, it's eigen problem. So h minus h1. We were able to solve this. We solved it. Trust me, we solved it. Because maybe Hamiltonian is very simple. Then, if you are equipped with the spectral decomposition of the eigenvalues and the projectors, actually it turns out that calculating any function of Hamiltonian, which includes the evolution operator, which is an exp of h, right, becomes trivial. This calculation becomes trivial, which you probably know, but let's spell it out explicitly just to show how this goes. So evolution operator, if you recall, exp, and we have our uniformly, absolutely convergent series for it, right? Which we now know what it means, allegedly. I kind of feel I know. And we have a Hamiltonian, which we can put here the spectral decomposition of this guy, ph, right, the power k. And typically you don't try to calculate everything, this series explicitly, right? We figure out some perturbation theory to do it. But as it turns out, if you notice that you have here just a sum of powers of projection operators, but projection operators are really easy to take powers of because they are potent, idempotent, thank you. Someone always has to remind me. Idempotent, yeah. Right, so this kind of, and they are orthogonal as well. So this simplifies a lot of stuff. So let me just write it down for us. You can write identity in particular, also decompose it in projectors, right? Because they are orthogonal and complete, because associated with observable. And this guy here, k1 to infinity, we have our factor here with time, and the factorial, which is responsible for absolute uniform convergence, right? Which we know what it means, allegedly. And the sum over k, where it's a k-fold sum then, over k different eigenvalues, k to h1, and we have our projectors, k h1, right? It's just rewritten it. And now we have the most pleasant of all activities. We just look at this and it's just a bunch of Kronecker deltas. This is the best feeling in the world, right? You just replace some monstrosity with with Kronecker deltas. Because hk is next to hk minus 1, so we just reduce it. So hk minus 1 times hk minus 1, hk minus 2, and so on, until we get to h2, h1. And because it's either 0 or projection operator itself, so we end up with one of those guys. Let's just pick here h1. Okay, so we reduced everything very easy. And now we can execute the sums, of course, and everything is good and proper. So this is trivial algebra, we don't have to follow it. But all in all, in the end, what we will get here is sum over h as h. We can extract this lone projection operator that survived all the powers, and everything it multiplies is simply 1 plus, is just numbers, okay, from 1 to infinity, minus it eigenvalue to the power k factorial, which is just simply, I have a shortcut here. No, how do you do? Scroll? Okay, this is how you scroll. H E I T H P H H. Only H. Right? And this is the most explicit we can get, right? It's just a combination of of our projectors and the numbers, depending on eigenvalue and time. So, so if you can solve eigen problem for Hamiltonian, you can diagonalize your Hamiltonian, everything is very simple, right? So why bother with anything why don't just diagonalize and then there we go, right? Why bother with anything else? This is like the ultimate trick, I guess.
Time independent.
Wow, okay, another guy who knows too much. Well, once we will get there, but Hamiltonians, as it turns out, they sometimes actually depend on time. And what follows from that is that there might not be one set of projectors that works for all times, right? And then it just wouldn't work. And that's one. But if we don't know about time-dependent Hamiltonians yet. We will next semester know about them. But the other stuff is that, okay, diagonalization is doable, but like exact diagonalization, of course, it's only for very simple systems, like 3 by 3 matrices. I think you can always do that. So dimension 3. For higher dimension, sometimes possible if Hamiltonian is very simple. There are some symmetries and you can do some stuff. But in general, you cannot count on analytical diagonalization. But that's fine because there is a numerical methods which can do it for you. And they are pretty, if you have strong hardware and good algorithms, you can probably take it very far. Although there are limits. At some point, stuff get too big matrices, and it's just unfeasible to diagonalize exactly, even numerically. But the other thing is that there is an issue with if you are just doing numerical diagonalization, you just get a table of numbers, right? Eigenvalues and coefficients of eigenvectors, I guess, in some basis. Just tables of numbers, big tables full of numbers. Well, sometimes it's enough because you just want to have this to calculate one thing, but typically if you do some research, you want to know how things work. So to know how things work, you have to have the ability to to know how it works basically means you want to know what are the causes. What causes this kind of effect? What is the cause? And to figure out the causal link between things, you have to have ability to intervene, to modify stuff a bit, right? So maybe you could okay, so I have this Hamiltonian, so maybe if I change this a little bit, this part of the Hamiltonian, would I still be able to get this effect? Or maybe it would be impossible. Then I could say that, this part actually causes this effect, right? But the only method you have is just table of numbers for a numerical diagonalization or whatever, you won't see your modifications, right? You won't see those effects. It's not transparent. So, diagonalization is fine and good, but it doesn't solve everything because if you don't have the ability to look at what are the effects of some changes of your manipulations on your models, you cannot answer this question why things are how they are. So that's why this is not the answer to everything. That's why you go for perturbation theories because perturbation theories, as we discussed previously on previous lecture, the point is that you there is some, you take a part of your Hamiltonian, let's say, you treat it as a perturbation, and you want to represent the influence of this part on your dynamics through something that's readable for humans, preferably in a form of pictures, diagrams. So something you can convert into actual quantitative predictions, but also qualitative ones, and something that can feed your deduction, reasoning, and imagination and stuff like that. So that's why it's not, diagonalization is not the answer to everything, because it's just looking at the table of numbers. I mean, if you are a savant or something, maybe that's enough for you. If you know, in the matrix, you could just look at the numbers. Oh, I see it, I see everything. But for less special people, you need some pictures, okay?
I had a question that exponential series and other series which are nice because they're absolutely convergent. But what if somebody wants to evaluate a function of an operator which does not have such a nice series expansion?
Well, if you don't have a series expansion, or maybe this, if your series is not super nice that it converges absolutely everywhere, right? Then maybe it converges somewhere. There is some radius of convergence and something like that. Then you work in there, inside your domain, and you proceed. But if you don't know what is your radius of convergence, then you might, for example, say, okay, I don't know yet, so let's assume it works, and we will worry about later if something blows up. But if you know that it's not nice, then you are in a special case. Maybe this is just a bad idea if you're working with something that's, if something is divergent explicitly, it's not converging because it's diverging. Well, then, is it maybe something is wrong on higher level here, or maybe you have to figure out what to do, probably what people felt when they were doing the quantum electrodynamics in the beginning, right? There was some blowing up of terms. So the short answer would be, if you know that you are convergent, radius of convergence, you just don't worry about it. You do as it is. If you don't know that, or stuff is divergent, then you are a special case, and special methods would be needed. You would have to be inventive. So there is no universal answer. But
for example, that's also a asymptotic series, which it's usually for cases where it's not convergent, but a few terms might be good enough for you. So it's another field of maths which deals with non-convergent series.
Yeah, so there's this mysterious, it's like legendary, mysterious concept of asymptotic series, which I don't have a good feeling for this. But this is because when you construct your perturbation theory, I said that you come up with some procedure for generating terms that you would sum up, right? And this terms, this sum, it might converge or might not. You have to check that, because the procedure it could come to you in a dream, for example, whatever. It's not like every procedure is must necessarily lead to convergent series because there was some mathematical law that it. Sometimes you come up with some procedure, and this procedure might lead to something wacky. Okay, and the asymptotic series is an example where you have a procedure, you have your terms, but the behavior of these terms is it works fine. You actually can check that your error is getting smaller, but at some point you just add more terms, and they are getting more and more nasty. It's and all of a sudden you're just getting more error, and it diverges, and it's what's going on here? This is called asymptotic series then. And it's branch of maths that deals with it, but I don't.
It's so bizarre. Why, if it is asymptotic, it is asymptotically diverging? Why?
Because it's
They have their definitions of what do you mean by asymptotic series. It's much looser than convergence. As a special case, you will get back convergence, and they have criteria for remainder and everything.
Well,
at least from a mathematical point, it is.
I believe it's also asymptotic because it's like typically you deal with them when you have like, because imagine you're doing your perturbation theory or series when the perturbation is small, small. So you like expansion in a small parameter, convergence in a small parameter, whatever. But sometimes you want to do like something that's actually infinitely, you want to go the opposite direction, something that's infinitely strong, let's say. Or you want to go time to infinity. And you want to like incorporate the effects of this infinitely strong perturbation in some perturbative manner. So it's like asymptotic because you are thinking, you want to approximate a value of an asymptote, where its stuff is, a limit of something goes to infinity. Yeah, so it's like one over parameter goes to zero.
Asymptotic series involves limits. For example, sin x is asymptotic to x as x tends to 0. And that's the language that they use. Yeah. So x tends to 0, that limit is always important. That's how the whole thing is what you call asymptotic behavior.
I don't know much about it. I have a book that I tried to read, but other stuff came in a way, and I never mastered it. If I ever will master it, but it's like interesting aspect. Goddamn, where were I? Why perturbation theory?
Yeah, why diagonalization?
Well, so diagonalization is good. Sometimes it's enough. Table of numbers. Sometimes you can do it analytically, small dimensional systems. But it's not the answer for everything. You need to. That's why perturbation theories are still good. So that was diagonalization. Just to say some things about it. So now let's move to the next section. Something completely different. Energy gap, and its consequences. We are just moving all over the place, but don't worry. There is it's like a Tarantino movie. We have like threads. There are not even in time, not linear in time. It's like we'll get there. So let me check time because that's probably time for a break. Oh no, it's actually not
so bad.
It's not so bad. Okay, so let's see. Okay, so let's start by let's say our Hamiltonian H. It's actually, we can diagonalize it, or at least in our minds. So we can form a orthonormal basis out of its eigenvectors, right? We learned that this is something we can do, and it's typically very prudent to do. So let's form an orthonormal basis, B of H, I believe, yeah, B of H. So this will be a collection of cats of this form with E, don't, maybe this is a bad letter. Don't confuse E with Euler number, okay? E is 1 from 1 to D, where D is this is a dimension of our Hilbert space, okay?
It's E from small energy, yes?
Yeah, energy, index of our energy. Woo! I needed a third letter that's not A and B, basically.
C.
But it just doesn't, it's like too close. So those eigenvectors, AB orthonormal, so AB, A and B can also be 1 to D, although we will maybe do something about it, just to fill all the gaps in this stuff. so they are orthonormal and they are solutions to eigenproblem, okay? And these will be eigenvalues then of our Hamiltonian.
Shifting from small h.
Yeah, I will explain shortly. So if you recall, it was many moons ago, that when we were first talking about eigenvectors, I was using this a little bit different notation. Okay, there were some eigenvalues were involved in the notation. Here I just, for simplicity, convenience, I will just an index. Okay, so each eigenvector will correspond to one of the eigenvalues. So eigenvalues depending on index. First eigenvalue, fourth, and so on. Sometimes there can be degeneracy there. Okay, so some, let's say, capital H1, capital H2 might be the same number actually. Those would correspond to small h. Because you have bases, you can switch to projectors, and the relation would be then PHH. So the stuff we saw above, that would be basically, you would sum over E from 1 to D. You would put here delta H, E, E. Okay? This delta takes care of the cases when there is degeneracy. Okay? Just pick out those eigenvalues which correspond to have the same value as small h. Okay? And I'm doing this because it will be much less writing if I have this notation, okay? Without some weird stuff. So we are basically enumerating all eigenvalues and not care that much about degeneracy at the moment, okay? And now, so we have our eigenvalues, energy levels, okay? Let's say, and now let's presume that there is a gap between levels. So what I mean by that? So let's suppose that we can order our energies in an ascending order. So E1 is the smallest, ED is the highest. And if we order them, let me write it that the Hamiltonian, the Ham has, yes, it's a Polish joke. Or no, it's not, okay. Ham,
It's also English, but Polish.
It's also English.
It's even Polish.
But it's even funnier in Polish. It has the energy gap. It's gapful. So if we order our Hamiltonian, so E1 is the smallest, E2,
So
right?
partial order?
Partial order.
So they can be equal.
They could be equal. Yeah. Some degeneracy might be involved. What we're doing like this, at some point we get to the HG, okay? And then there is HG plus 1. HD. And this is much bigger difference, okay? So let's imagine that. So this difference, that would be the energy gap. So we can say that it's big. So the difference between those two levels, maybe it's much bigger, let's say, or bigger than the whole spread of, let's say, energies below the gap. That's why it's big, let's say. So it's, there is like some energy levels and then, or maybe, whatever, something happens above. So we have energy gap and gap. Let's invent a name for it, omega. And this will be just EG plus 1 minus EG. Okay? A G for gap, letter. Which will also we can alias for this g plus 1g, small omega, and this capital omega is such. Let's say that it's for now being we can assume that it's much bigger than the spread of energies below the gap. So I would write it like this, because I'm introducing another notation convention. This small omega. What's this? What's this guy? Well, this is a frequency. Frequency associated, just frequency. It's associated with energy levels. And it's, so omega BA, that would be defined as HB minus HA.
So you're using the same notation for, different notation for saying capital omega and small g plus 1g.
Yeah, so
basically same, right?
Because
why did you write capital omega?
Frequency is between any two levels.
Because it's special.
Right, but this one is special because it's big, because it's a gap. So it's also omega.
No, it's confusing because to read it 1 1/3, they are saying that they are equivalent. So then how can you write omega much greater than small omega?
Sorry, I should.
But it's a small omega of G1, not G1, G plus 1G.
Well, if I say that, right, so
You can.
because let's say I defined it on the side, what small omega is. So this guy here is just Eg minus E1.
Yeah.
So this would be the spread of those energies below.
And what is capital omega?
It's this difference, this gap.
Maybe we deserve it.
Okay. It's not a picture power. But for me, both are the same thing.
Yeah, the alias. This is alias. I mean, this is all the same thing. Just symbol, because you imagine we'll be using it a lot. So if you want picture, Hubert wants picture.
Yes.
So the picture we're having is something like this. So that would be
It's like two energy manifolds.
H of E, okay, and this would be E G plus 1. This is E G, okay, and this distance here,
Omega.
this is capital omega, also known as omega G plus 1, comma G.
Thank you, Hubert. Now I know it.
So they are the same thing, right? Then how did you write that last statement? Capital omega much greater than.
I mean, easily. I just
small omega G.
two bars, two dashes, and
Because if they are the same thing, then how can you say one is larger than the other?
No.
That's
You
my
have G dot
comma 1.
So this is the spread.
There was a
It
confusion.
was the confusion.
It's a broadness.
See,
You can draw that one as well on the picture.
Okay,
It's the
now,
broadness
that was
of
the
this
confusion.
lower manifold.
Yeah, if I
Tutaj.
Maybe another color.
that would be E1, right? So this distance is omega G.
Okay,
One.
so it was my problem. Yeah, because I read it as the same.
Yeah,
that's why
I am blameless as usual.
But
I'm
in
just
this
a-
picture,
I'm just a
omega G plus 1G is not bigger that much.
What?
It's about the picture.
The
It's
picture.
okay.
The picture is okay. I am blameful.
Picture is it's a general picture.
Yeah. Actually, okay.
It's a parametric picture.
Yeah.
It's a parameter. It's a logarithmic scale. let me whistle out of this. So energy gap.
Very good.
So this energy gap would be like a key feature, okay, for our purposes. So now maybe investigate what it could mean for us, because I don't know, it's just eigenvalues, whatever, who cares? So let us inspect some multi-time correlation, some correlation function, because we know, Hamiltonian generates dynamical. The evolution operator. Purpose of evolution operator is to calculate correlation functions, which actually then, those guys actually represent some physically observable effects or phenomena or whatever. This is, so it has to be put into somewhere, right, to actually observe consequences. So let us calculate some simple correlation function. So there will be some observable y, because t plus x, y, x, because, just because. And let us, for simplicity, let's consider a two-time correlation function. If you don't recall what the notation was, don't worry, we will get to concrete letters, concrete inscriptions in a second. And let's, as an initial condition, let's take something very simple, that our system is initializing one of the below gap energy levels, okay? So we can represent this guy by PA, 0 minus, where PA, its reminder, is a projection onto A, and A is, so when you see A, that will be below gap index, okay? B will be above gap index, just
So A is below and B is above?
Yeah, so whenever, just
A is below and B is above.
oh God! I didn't think about that.
Below.
Okay, let's change this. Okay, yeah.
We will make this lecture
B.
5 minutes faster next time. Make more sense.
B,
Low.
B,
Mathematicians will be happy.
low.
And now we have below.
A, bow. So A will be greater than G.
Above.
Above, below. Yeah, that's good. Oh, I like
What
it.
kind of low it is?
G plus 1.
Below.
Some rapper nickname, you know.
Yeah. Should maybe A bigger than G plus 1?
But it's greater than G.
Okay,
Greater than
but
G.
it's including G.
Well, okay, that's true.
It could be greater or equal to plus one.
Yeah, that's true.
We're trying to like improve everything here. It's this is perfect. Okay, so let's. I mean that's why we are taking so much time, but it's you know, at least we are having fun. So just to, if you don't remember the notation, what it translates to, it basically translates into a Heisenberg picture of observable y at time t2, Heisenberg picture of observable at time t1, and the projector comes in, B, boom, okay? And just to remember Heisenberg pictures and stuff, trace, let's do step by step. Now I have to, in my mind, transpose A and B from notes. I'm sure I will fail. So E T2 Y, E minus T2, Heisenberg picture, right? I'm just translating. I T1 X, I minus T1, and the projector on B below, right? And now the trace, we can execute trace by doing the sum over all the eigenstates, right? Just because it will be simpler, because we already have here projector, so it will pick out only the B movie. Ah, the B movie. Ah, right. Ah, okay.
Sorry, I'm not sure. Should the exponents have like the Hamiltonian?
Yeah, they should. Yeah. Oh my God, I forgot the most important. Heisenberg Hamiltonians. Oh, sure. I got so excited by B that I forgot about H. I forgot my alphabet. Yeah. So we put this guy here. Okay, let me do step by step. E minus T2H. Do I want to merge them? No, I don't want to merge them. One more thing I will do. I put here the identity. I put here identity, which I decompose into projectors onto my basis, right? This standard trick. I'm doing this because we are assuming already that we have diagonalized the Hamiltonian, so we basically want to exploit that to our benefit. T1 and B. B is A is B. And now we can start doing crazy stuff. Yeah. So this we should simplify, and it does into a sum. E, this is the identity we put here, and we will have B, Y, E, X, B, and here all the
eigenvalues.
yeah the operators, the evolution operators. Then we can act with them on the eigenvectors, which basically converts the operator into corresponding eigenvalue. So we turn all the evolution operators into numbers, and those numbers will nicely collect into the following expression, T2 minus T1. Okay? Which is, this guy here is the frequency, omega B E. Okay? Okay. And one more thing. These guys are basically matrix elements of operators Y and X. So we can final touch ED. Because I had a notation for operators for matrix elements, which was this square brackets, just to not confuse, observable from operator from matrix element. EB, or we can BE conjugate, because observe Hermitian. So there is this symmetry. I omega B E T. Oh, this is the correlation function. But wait, there's more, because that's a correlation function. You know what? Let's take a short break, and after the break, I will tell you what's more.
Okay. Mysterious.
Yeah.
Breaking climax.
Yeah. So 5 minutes, if we can handle 5 minute break.
No, but we will get crazy.
With the power. Okay, so let's continue. So we calculated our 2-point correlation function, but it's like I tried to impress it on you. Maybe it wasn't super clear back then, but a correlation function itself, it's not like by looking at the correlation function you get the description of some effects. Okay, it's like it's a part of some description. If you recall the Kubo formula, which I gave as an example of application of correlation function, you remember Kubo formula?
No.
Remember the name.
We know Kuba. But we don't know his form.
Kubo formula. So it was a linear response thing, okay? So there was you perturb a system with some external field, let's say weak field, and you measure how the deviation of some observable expectation value, some observable from unperturbed versus perturbed situation. And if the perturbation was weak, this is quantified by this kind of integral where you have so this described the perturbing external force field, and here is a two-time correlation function, okay? So correlation function itself, it's a component of effector, let's call it, of an effect. So the thing, let's say the prototypical thing you would do with correlation function, you will integrate it with some kernel, which could represent some force field, let's say, or something like this. So let's do that. So let us do that. So this is a core, the correlation function, the carrier of the information about dynamical properties of the system. And now let's extract some effect from it. And to use the Kubo formula as a prototype, let's just integrate it over time, this kind of two-time correlation function. So let's do it. I came up with this name effector, which I like. It's like sounds very scientifically, I don't know, sounds smart. So let's call it an effector. I don't know, it sounds cool. So let's calculate an effector. It is some function f, s, and let's plop in our correlation function. It was y, t2, x, s plus 0 plus p b 0 minus, because we know it depends on the time difference, so we can just simplify the problem by shifting our time variable to just the difference of time. Let's call it s. This is what happens in Kubo formula as well. And let's take absolute value of this guy, because we want to estimate some stuff. We want to estimate the effects of the gap. So this guy then would be equal to sum over E that goes over all the levels, all the energy levels. We have the Y, B, E, X, E, B, and we have a integral f of s, E, I, omega, B, E, S, ds. Okay, so the frequencies, it's like a Fourier transformy stuff is going on. So that's one step. Now let's okay, let me move here. Let me split the sum now onto A and B, or B and A. Oh my God! Now I have to do the flip.
But it's for the best. It's all best.
Yeah, it is for the best. I agree. So we have this, and A greater than G. It's gonna be so difficult. B prime, I guess. Let's rename the. No. Not yet. We are still at this sum. Let's split our sum, one sum into two sums. Oh. Not yet. Don't change the thing yet. YBE, XEB, and the integral. Omega BS, ds. Okay, and now what do you want to do? Oh, just do the calculations. Now let's. Okay, so we have here absolute value. We have sum over indices below the gap, so B low prime, because B is reserved for the initial condition. And let's leave this guy, B prime. B prime. It's like transformer B prime. Bumblebee prime. It's probably even the thing. Is there a bumblebee prime?
No, it's only Optimus Prime.
Well, there were a lot of primes. It's a title. You don't know your Transformers lore.
Yeah, perhaps.
Maybe. B prime, yes. And then we have a sum. So this was below, and here we have above. So A greater than G. Y B A X A B. And here, let me do a trick. Because this guy, this integral, I can do integration by parts here quite easily, right? Very, very simple stuff. So let's do at least one integration by parts. So this would give me f at t, the end point, I omega b BA at t minus f of 0 divided by I omega BA, okay? Minus 1 over I omega BA, and the integral reforms itself. Omega BA S ds. Okay, this is what I wanted to show you. Because what is this BA here? This is the difference between, the frequency between the level below the gap and above the gap. So one of the things we can say for sure about it, that it's no smaller than the gap. And the gap is big. So we have here in the denominator a big frequency, probably larger than the gap itself, which is already very big. Okay? So this whole thing is less than equal a effector doing its thing below the gap, in the subspace below the gap, just does something. Stuff oscillates, stuff Fourier transforms here. This is all nice and good. The frequencies are moderate. And we have here a correction that's, dumped by the inverse of the gap, which is a small parameter in our theory. A greater than G, absolute value, Y BA, X AB, absolute value, well, times the thing we calculated, T E omega BA, T minus F0, plus corrections, big O, omega minus 2. Okay? So this is what I wanted to show you, that if there is a gap, right, then the effects the gap has on effectors, on things that we can observe, is that there is because this frequency is so big, right, it comes in as the bigger the gap, the smaller the correction from going across the gap, right? Because here you have matrix elements that connect the energy levels below and above the gap, right? And here you have matrix elements that connect levels below the gap only. And thus those frequencies here are moderate. They are not too fast. But the frequencies that comes from the connecting across the gap are big and large, and they're very violent. And you can estimate the effect of this violence of theirs by doing this integration by part to see that it's like it introduces a damping 1 over omega. By the way, doing this integration by part, this is one of the like a standard methods of doing an asymptotic series for something, for effector actually. By the way, and this is an asymptotic in the gap getting big to go into infinity. Okay. So the technical explanation for this is those oscillations here, BA, so across the gap, they are fast. So this is like the effect. We integrate some function that's kind of smoothly behaving with very quickly oscillating this phase factor. The effect is that it's getting like averaged to 0, right? Basically. There are a lot of approximations, a lot of like estimates that use this random phase, fast phase effect into account, you know. And more physical explanation would be that, you know, the going from level to level, going to so this transition that kind of like symbolized by this matrix elements here, it's like costs energy, you can imagine. Because, you know, you go from, let's say, level 1 to level 3, you have to pay the price in the difference between those energy levels, omega 3, 1, okay? That would be your price. And now the gap introduces a high tax on going across it, right? Because you have to, you jump from one level to another, but there is the gap has to be paid. So if you are like, you know, boiling, evolving below the gap in this subspace where we initialize our system, you know, you pay energy, you go from one level to another, there is, you know, it's fine. But now going above requires much more energy, okay? And this makes it less likely than just staying below the gap. Okay, so that would be like a physical explanation. If there is a big tax to be paid, the system won't like to do that. It will like prefer to be, you know, where the stuff is cheap, where the inflation is not too high.
It's economy.
Yeah, it's an economic argument, basically. So, so you know, there are, as we can see, there are still ventures abroad. Across the gap where the prices are high, but you know, this is they are dumped. We can see that the more pricier it is to go up, the lesser the contribution to the overall effect, right? This is like the idea. A lot of energy, the less energy to be paid, the more likely the thing would happen, and this is so neglecting the high energy cost processes probably does not introduce a lot of error in your calculations. So, and this is like the core of this idea that so if you have this system, the situation when there is this gap, there is price to be paid, you have this effect that the errors are small when you neglect going above, going across the gap. So what if you just completely, you know, just forget about this higher energy subspace altogether? You know, so this comes in, introduces this idea that maybe we can like think of an effective theory describing our system where everything is confined into this subspace below the gap, you know? And then you just ignore everything that, you know, all the ventures across it. So, and this is this is like a the idea of low energy effective theory, which like formally you can imagine that what is happening. So you have your original Hamiltonian that has like energy levels of a d-dimensional system. And you basically like, let's replace it with an effective Hamiltonian for a system that's smaller dimension. When you have B, G1, EB, EB. Okay, and you basically ignore that there is some universe in a higher dimensional space. So you take your big theory, d-dimensional theory, and you reduce it to some effective theory in g dimensions, which is smaller than d. And your justification is because there is an energy gap, and all the effects for crossing the gap, they are taxed with high energy costs, and thus they are less likely to happen, and thus the contribution to anything could be neglected to some good approximation. The bigger the gap, the better the approximation. So that's like the idea. Okay, and now let's try to formalize it a bit. Okay. Some questions to this?
So till now what we did is we have a Hamiltonian and we know how to solve it. We got the spectrum and we just looked at the spectrum and said there is a gap.
Yeah.
And we identified a low energy space.
Yeah.
Okay.
Yeah, that's what we could do. So, okay, there's more to it. We know, but it's like it won't be important. I mean, this of course works if you are you consider initialization that's below the gap, right? Because then you will live below the gap.
I can ask like, how are you guaranteed that you will stay there in the low subspace?
No, it's there is no guarantee. Because there is this correction here. This correction is small, right? So the correlation functions or the effectors, will have contribution, but it's small. If omega is big, you can neglect it. This is the argument. And one more thing to note, that it's actually not essential that this is lower energies, the subspace of lower energies. Because you could equally well do it for this higher energy subspace, because what matters is an energy difference. Right? The frequency is big when the energy difference is big. But if you are in lower energy subspace or higher energy subspace, the differences between high energy levels may be very small, right? They are big in comparison to low energies, but within high energy subspace, the differences might be small and the frequencies are small.
So what do you mean that is we don't have, so let's say we have one block, second block and third block.
Yeah.
So we can apply it to the second block as long as it's separated from block 1 and block 3.
Yes,
okay.
yes. Although like most...
Could you please tell me one more time? Sorry.
You have a bunch of energies, block 1,
let me draw.
then you have block 2, then you have block 3.
Okay.
So all the three blocks are separated.
So what
You
Sarah...
can apply this, you need not apply just to block 1, which is the lowest energy subspace. You can equally well apply it to block 2, as long as it is separated from 1 and 3.
You see...
Block 3, but from block 2, you cannot go to block 3, but you can go to block 1.
No, he said you have to stay within block 2.
The point is that imagine that you have this structure, and this is a big gap. It's like omega that's much bigger than the spread of those here and here, let's say. And here's another omega prime, it's also big, right? And so this would be the lowest energy.
The ground state.
Yeah, ground space.
Let's say this would be like moderate energy.
Ground state 9.
This would be high energy. But if you initialize here, initialize here, you know, you will have some things will happen inside this block because the differences between those energies, absolute value of those energies is large, but the differences are small in comparison to gaps. But the transitions to here or to here will be penalized by the tax of gap. So you can isolate your block and have effective theory for this middle block, even though it's not the lowest energy.
So,
It doesn't matter what's the energy of the block, it matters what's the spread.
I understand the gap is what really matters. I think it's what causes probably the destructive interference with the higher frequency phases. But physically, why wouldn't a higher energy system be able to tolerate
Yeah,
lower
exactly.
energy system?
like, why want it to relax to the lower subspace?
There is no relaxation
Yeah, that's the thing. That's the
process.
doubt we would have.
Uh,
I think, yeah.
There's
No,
no temperature,
Because we are not,
there's no
yeah, exactly.
relaxation.
We are not connecting it to anything for such a relaxed. So the old processes will be captured by the transitions allowed by the Hamiltonian.
I mean, this is
and you are suppressing that to lower. space.
typically you consider the lowest energy because you also consider the relaxation. Because why are you initializing this block or the other block? You know, probably because of thermalization, right? And the thermalization, the temperatures are low. The thermalization will bring you to the lower energies. So you will end up in the lowest energy block by default then, okay? However, there might be some reasons why maybe you excite your system as a part of initialization, and you're actually in the middle or in the high level, right?
Apparently, in my research, I'm in the highest level, and from this I do.
Oh yeah, because Hubert is actually he actually uses Schrieffer-Wolff transformation in his work.
Yeah.
So he's like a guy who has hands-on experience. So we can use his wisdom to fill the gaps, big gaps or small gaps.
So if I understand correctly, what is happening here is you can indeed have a matrix element from middle block to the lower block.
Yeah, you
but
can.
I think that will be suppressed in the order that we are working. So we can.
Yeah, I mean it will be suppressed by the difference of energy between blocks, which is if it's gapped. The sign doesn't matter essentially. If it's big negative number or big positive number, doesn't matter. It enters, the magnitude what matters. So that's why it's just, you almost always will be saying that low energy subspace, high energy subspace, and this is like typically how it's used. But bear in mind that it's nothing perverse. If you are, you are doing effective theory for a middle, high energy subspace, and you are getting rid of the low energy subspace. If your context requires this, that's fine. The same theory would still apply. Okay, it's like what is positive, it doesn't matter. It's only the differences matter, the magnitude of differences. Just to bear this in mind. Although we will stick to this nomenclature that we are in low, which is natural if you think about processes like thermalization and stuff. Okay, so that's the ideological, that's the propaganda part, basically.
Well-fight propaganda.
And now for something not completely different, but very related. 3.3, Schrieffer-Wolff perturbation theory. Theory. That's the name of the game. Schrieffer-Wolff perturbation theory. So now suppose, we have our gapped system, we diagonalize it, right? So it's like choosing where we sit, it's just whatever we want. We have all the power in the world. But now let's suppose that there is a perturbation was introduced to our system. So introducing the perturbation. Introducing the perturbation. So we moved from H
That's right.
to H plus lambda V, the perturbation. And the strength, the lambda parameter is to help us keep track of the strength of this perturbation. So this is real, previously we had we tried to cobble together perturbation theory for the evolution operator when it was just Hamiltonian. It's so I guess Hamiltonian is a perturbation. But now we are really considering a situation when there is a perturbation, and this is key. And we have a perturbation theory that really treats this V as the thing that has to be involved in some kind of series, perturbation series. So the thing we will assume here, that this perturbation is weak enough so that it doesn't close the gap. Okay, we still want to have a gap. Or maybe even to be safe, let's assume that it's much weaker than the gap. So it not only doesn't close the gap, it's not even close. So, so we will assume that basically the magnitude, lambda V, is much smaller than omega divided by 2. Why this argument works? Because so we have a Hamiltonian, right? It has a spectrum, eigenvalues, right? If you add something to Hamiltonian, like this V, it will, the new Hamiltonian, perturbed Hamiltonian, will have its spectrum as well, right? But if you want to estimate how much this perturbation will shift your original eigenvalues, well, the most it can do can shift them in either direction by the norm of this operator, because norm is connected to spectrum, if you remember, right? So if we are here, right? Drawing it in vertical is just so wasteful. So that would be original G plus 1, and that is original G. So I add this guy here. So this can be moved at most by lambda V, okay, by the norm. But this can also be moved by the same, by lambda V, okay? So if you want to prevent them from closing the gap, you would require that this perturbation is smaller than the half of the gap, right? To avoid the problem that one is dropped down, other is increased, and now they overlap, the gap is closed. But we want to prevent closing the gap, but let's be more greedy. Let's demand that it's actually not even close to closing it. Just to be safe.
It still has to be the gap, the large one.
Yeah, there is still a gap. So the ideology, the propaganda still works. There's still a gap. So this is our assumption here.
Is the H the lower H or the total H? Like, is a Hamiltonian just a Hamiltonian for the lower energy or for the whole?
For the whole. If it's effective, then it will. I will make sure to. I will make sure to let you know. This is the complete everything. And now, if so, the lambda is small enough, so we have this magnitude is controlled. The V itself could be whatever Hermitian operator we want. But just to simplify a bit things, let's assume that the only thing it does is actually connects the high energy levels with low energy levels. So let us assume that V is of this form. So there is a sum B less than G, A greater than G, and we will have a matrix element, what do I want, PA, BA plus, to make sure it's Hermitian, BA, AB. Okay, so it connects the blocks, but it does nothing inside the blocks, just to simplify things. If there was a case, there was a perturbation, let's say W, such that it would actually live inside the block, low energy block. So W, that would look like, you know, you have B prime below the G, and you would have W, B prime, B prime, okay? So let's suppose that this low energy subspace is actually small enough dimension that we could just take this H plus lambda W and just rediagonalize this guy and get our new energy levels, okay? And then we would add V to connect them and to start from there, okay?
Shouldn't it be AB in the Hermitian conjugate part? For the transpose?
As a lower index. Lower index here.
Doesn't this take care of it?
No, that's just
That's
a
conjugate.
conjugate.
It's not conjugate.
Yeah, but
Transpose.
That one is yeah.
It just takes the complex conjugate. It doesn't flip the index.
yeah, but it's,
And
Hermitian means that if you flip, the conjugate comes up. I think this takes care of it.
Above you actually wrote down before the break and you flipped the index.
You know what? I'm not sure. Let me just write like this, and we are happy. Okay. And there is it's Hermitian conjugate, so they have to be connected via.
Yeah. Okay.
If you flip, you pay.
Sorry.
Whatever. So we are not including perturbation inside the block just for convenience, and we imagine that if it was there, we just rediagonalize everything. At some point, we will, do the full perturbation theory. We will explicitly involve this guy, but for now, it will just bother us unnecessarily because there's nothing interesting happening there. Because the real deal, actually, the connection, when Hamiltonian can now have itself transitions between subspaces, this is something we have to contend with. Have a transitions across the gap in the Hamiltonian itself. That's like the problem to solve. If you want to preserve this gap picture. Okay. Yeah. Okay. This is so the gap gave us the reasons to think about constructing effective description of the lower dimensional system, right? So we want to preserve it somehow, even though there is a perturbation, right? So there is a couple of things that's going on. For one, the perturbation, of course, so we had unperturbed spectrum, which has gap in it, and the adding perturbation where shifts it somehow. We already discussed it, right? So we have a spectrum of H plus lambda V, right? But we are not worried about this guy. It shifts numerically the energies, but it doesn't close the gap. We still have a gap. However, what is more, so because of that, we can at least write the spectral decomposition of our Hamiltonian, perturbed Hamiltonian, and it can be broken down into below and above gap, pieces, parts. B plus A greater than G. A, EA, EA. So this would be the eigenvector of the perturbed Hamiltonian, okay? This would be eigenvalue, the energy. corresponding to this eigenvector. And because the perturbation doesn't close the gap, in spectral decomposition, there is still a division between the lower and higher energy levels, and the energies, G, or maybe even EB minus EA. Oh no, it's flipped. It's flipped. B is below. E is above. Right? This is like greater equal to gap over 2. Okay, so there is still gap there. So this is fine. This is fine. However, the issue is that although we know there is a lower and higher energy subspaces, but we now don't know where they actually are, because the perturbation shifted energies, but it also shifted the eigenvectors. So everything is a little bit rotated somehow, or maybe a lot. So we can write this decomposition formally, but we actually don't know what it is.
I think if it were rotated a lot, it wouldn't be a perturbation.
I mean,
that's
what we believe, right? It's not so much different from the unperturbed eigenvectors, but it is some difference, and we have to know it to actually execute any calculations with it, right? Yes. So one way to know what those eigenvectors are would be to basically solve the eigenproblem for the perturbed Hamiltonian, full d-dimensional eigenproblem. But this is the thing we want to avoid. Okay, we got lucky with H, non-perturbed H. Someone gave us it. This is our basis for everything. But now we don't want to deal with actually new diagonalization. This will be hard, difficult. We want to do some perturbation theory to solve it, actually. Not to...
That's actually what I'm doing. Diagonalizing the new edge.
Because Navit is also doing Schrieffer-Wolff. At least, yeah, and they are using different modes and trying to diagonalize stuff.
You don't want to.
For some reasons. Maybe we can discuss it later. We'll discuss later the modes of usage and their trauma. We'll ask them for opinions. Okay, so we don't want to explicitly diagonalize this perturbed Hamiltonian to get those guys, but we want to get there somehow. Okay, we want to know where those subspaces are and the energies also. We want to know those as well, but without solving eigenproblem explicitly. So the thing that we can hang on to is that if we manage to actually diagonalize perturbed Hamiltonian, right, we would be able to construct a basis, orthonormal basis for it, plus lambda, and it would contain all the E eigenvectors, right? Where E goes from 1 to D, d-dimensional problem, orthonormal, and so on and so forth, right? And the thing about orthonormal basis is that each orthonormal base is connected to any other orthonormal basis through some unitary transformation, right? You can always switch bases with some unitary transformation.
Yes.
So in particular, our original eigenvectors are connected to those eigenvectors which we do not know yet via some unitary transformation. So we can write it down as a eigenproblem. Wait, basis transformation first. Basis transformation. So there exists some U unitary that takes us from BH to be h plus lambda v, okay, such that, and let's call it e to s, because unitary transformations can always be generated by some generator by taking exp of it. Is it clear that this is true? Do we know that it is true?
Say again?
That every unitary transformation is generated by some operator?
Yes, for some
It's
unitary.
from experience.
Okay,
There was some statement in mathematics.
yeah, there is. This is a statement about special unitary group,
Yeah.
SUD.
The general-
Unitary transformations form a group, not semi-group, proper group. And it is
generated by an
Lie group, so there is a generator. There's Lie algebra. I mean, there's a whole shebang. Okay, so we can this transformation can be parameterized by this generator S, which one moment, and it is such that ES when acting on E. Okay, don't confuse Euler number. This will turn us into EE, okay? And the inverse transformation takes us back. And you might be suspicious a bit. Is this, how come this guy is dagger of this? Because S is anti-Hermitian. S dagger is minus S, okay? We could also go for a Hermitian generator, some G that is Hermitian. And then we would have IG. That would be our transformation. However, as it turns out, it's much more convenient to use anti-Hermitian. So basically S is S, you can think of it, it is I times G. Okay, that's what. So Hermitian operator times unitary unit. It turns out that it's much more convenient if you don't keep this I floating around. It's just mess. If you try to do calculation, it's just ugh. It's just ugh. So it's better to keep anti-Hermitian, and everybody does it, and everybody calls it S. Okay. So now we have this transfer. It does exist. It must exist, and so we have another incarnation of eigenproblem. Eigenproblem in generator representation, which would be. So we want to take our perturbed Hamiltonian and we sandwich it with our basis transformation. Okay, so we take operator and move it to different bases. And this will perform the diagonalization for our guy. Okay, so this is the eigenproblem, but in generator, because solving this eigenproblem amounts to finding S and eigenvalues, basically. Okay, so solving this is the same as solving any other incarnation of eigenproblem. Okay, it's the same level of difficulty. However, and this is not.
Can I ask something really quick with annotation? Are those eigenvectors or projectors the same as for the previous Hamiltonian?
Yes.
Yes.
And perturb.
Okay.
Yes. So you can imagine that this is true. I mean, this is a spectral decomposition for eigenvectors of perturbed Hamiltonian. Okay. And now we say, okay, there is a transformation that takes us from the perturbed eigenvectors to unperturbed, and we just applied it here. So if you put here the perturbed, it will bring us here. Okay?
Unperturbed to this.
Under what?
From unperturbed to this energy, not from perturbed to this energy.
Uh,
To cut.
From perturbed.
From unperturbed.
Eigenvalues are the perturbed.
E to power S is bringing from
Eigenvectors are not.
From the
unperturbed to perturbed.
unperturbed to
Perturbed.
Yes.
I mean, this is always difficult. Should I put minus here
Yes.
and plus here, right? That would be consistent
Okay.
with this. Or minus here. I mean, okay, this is classic. This is all. There's always some problem with the sign. How you defined it, okay? But the point is that we want to because we know the localization of those subspaces, so we want to stick to them, right? That's why we want to this direction. So again, solving this guy, finding S that executes this and those eigenvalues, this is the same as finding the projectors. I mean, it's yeah. We don't want to do this explicitly because that would be, we want to avoid solving every problem. But this form allows us to try to find a perturbative solution to this S problem. Okay, and this is what the Schrieffer-Wolff problem is. Okay, you are looking for S such that it executes this, and you look for S in the perturbation theory approach, which simply amounts to. So you do. We are looking. We are trying. Oh yes, that's two difficult words. Solve it perturbatively. Solve it perturbatively. It was also difficult. So there will be a couple of steps. Step one, and this is like, and this is kind of like the first push. So this is a general approach. Okay, let me say this. You take your you have some problem. Maybe it has some defining equation. Like this. You want some transformation that does something, and you put it in the form of there is a transformation here, and there is a effect what it produces, right? So that would be like this defines your goal. The step one, if you like trying the first approach at doing perturbation solution, step one, perturbation series representation. Perturbation series rep. So you assume that your solution, the things you are looking for, so in our case S and the energies, they can be represented as a power series in the perturbation strength, which is lambda in our case, which you can treat as a variable formally. Okay, so we shall assume that S can be written as a sum k from 1 to infinity, lambda k s k, okay, and energies, each energy be it also a series. This one I want from 0. Lambda k e k p. Okay, let's assume that we can do it. This is like if you are trying to do something, this is like a good first step. You don't worry about convergence. You don't worry about nothing. You just let's do it, YOLO. You just let's try where it will lead us. If it leads us somewhere sensible, then we can backtrack and prove what is the radius of convergence and all this stuff. But this is like the first move, which you can apply to many problems, okay, this kind of reasoning. So you assume, step one, you assume that this, you can represent it in this kind of series. which then leads you to the step 2. Step 2, power series expansions, I call it, power series expansion. So you have S and E have series representations. So now you imagine you put them here into your problem, your founding equation, and you do the Taylor expansion of both sides of this equation, which in our case leads to the following expression. E minus D1, E0, E plus lambda E1, E plus lambda squared, E2, E plus blah, 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 projector, equals H plus lambda V plus S commutator with H plus lambda square S1, sorry, S1, first order, oh, wait, error. Why is it here? No error. Very good. Yeah. I'm stupid. I'm so stupid. Low IQ, smooth brain. Commutator with V of first order S plus second order S with H plus new line, 1/2 of a nested commutator of S1 with H plus and higher orders. Okay? This is unnecessary. And now the exercise for you. Actually prove that this, when you do Taylor expansion, you actually get these commutators. Okay, just do the algebra. Expand the x, the left x, the right x, and collect terms of equal order in lambda, and see that it has this nice Lie algebra, Lie algebra structure.
Baker-Hausdorff formula, right?
Yeah, BCH.
I mean, if you want, or just expand and just collect terms. Or you can use whatever theorem you want if you know some stuff. But it's just to see. Okay, I won't be calculating here. Clearly, I don't have time and no inclination. Yeah. So we expand both. So assume that things we are looking for have power series representation. Going back to our founding equation, substitute those series and expand it. Power series, the equation, left and right hand side, and then you have third step number 3. Step 3, compare orders. Compare orders. And the final step is you generate an infinite system of equations by taking the stuff on the left that's multiplied by the lambda to certain power and finding its partner on the right-hand side. And for this equation to work for any lambda, because formally we can treat lambda as a variable. So, the stuff of the same order in lambda has to be equal for the whole expression to be equal. Standard trick with polynomials. And also a standard trick with homebrew perturbation solutions. So we can compare orders. So in our case, the zero order, we get an equation of this form, E0, E projector equals H, zero orders. You just look, okay, this has lambda to the power 0, this has lambda to the power 0, equal them. The first order, so stuff proportional to lambda, so this and this. Another equation. No, we don't have to, we can skip writing down the lambdas. It's already built in. Equal V plus S1 H. And this makes sense because H is like zero order because it's unperturbed. V is first order because it's this is perturbation. S1 is a first order by assumption, and E1 is also first order. And second order, you can see what's up, and you form the infinite system of equations. So now, once you do this, you can proceed and try to solve this equation because now the initial problem is difficult. But now we've broken it down into manageable chunks, infinite number of manageable chunks. But we can go if it's not malformed. Okay, in other words, if our assumptions about series expansion actually were true, so the convergence and stuff like that is actually true, we should be able to go order by order. And this whole system will be soluble if to solve order k, we don't need to know the solution to higher orders. So you can just go from the lowest order, and this will be enough to proceed. And you can iterate order by order. If this is possible, the equation is of this form, everything and the assumptions worked, you can do this iteration, and at any moment you can say, okay, I'm done. So I'm done at order k, I don't want to proceed more, and this would produce for you an approximation of order k. Okay, so this is like the standard procedure. And we are over time for sure, standard. So we want, I want to solve to the second order this for you, to show you what it looks like, but let's do it on the next week.